Your last section in Chapter 10 is going to start focusing on friction, air resistance, and gravitational forces. Now, Newton's first law. Newton's first law stated that objects in motion tend to stay in motion and objects at rest tend to stay at rest. So my question to you though is, if objects in motion tend to stay in motion, why is it that you push a ball or you let off of the accelerator on a car, why does its motion tend to slow down? And hopefully you said that is because of friction. Friction is just going to be any force that opposes the motion of an object. Now, the result of these two surfaces that are coming into contact with one another, the result of these two surfaces opposing motion is going to be thermal energy or heat. There are two factors that are going to affect friction. Number one is going to be the types of surfaces. If I kick an object on the floor or on carpet, you know that it's going to go a certain distance. But if I kick it on ice, you know that it's going to be able to travel a lot further. The other factor is going to be how hard those surfaces push together. I mean, if I take my hands and I rub them together, I feel a little bit of heat. But if I really push hard against my hands, I get a little more heat or a lot more friction interacting. Is friction good? Depends on what it is. If we're talking about automobiles, it gets rid of some of the efficiency. That's why we have low gas mileages. But if you think about why we put gravel on icy sidewalks, it's because we want to increase the traction so we don't slip and fall. When we go ahead and we talk about friction, there's going to be three types of friction. The first one is going to be fluid friction. That's the reason why we add oil to automobiles. Basically, it is putting a liquid between the two surfaces that are going to be in contact with one another. Number two, that's going to be sliding friction. That's actually the two surfaces touching one another. When you're driving in an automobile, the tires are literally touching the pavement. So again, sliding friction is those two surfaces literally coming into contact with one another. And the last one is going to be rolling friction. It's just going to be when there is a round object between the two other objects and it's going to roll over the surface. If you think about the ancient Egyptians, when they were moving their large blocks to form the pyramids, they typically took some logs and they put the large blocks on there and they basically rolled it over the surface and getting it to move or transport from one place to another. So when we talk about this ball, and I take this ball and I let go, of course you've told me before that it's going to be gravity that's going to pull the object downward. Gravity's value is going to be negative. The negative is just going to indicate downward, and it's going to accelerate downward at that negative 9.81 meters per second squared. Freefall is going to be a force where it is only gravity affecting the object. So we're not talking about any type of friction, we're not talking about air resistance, but if we went to someplace like the moon and we dropped an object, it's only going to be gravity that causes it to fall downward. When we talk about free fall, again looking at the acceleration of it, notice it is a meters per second squared, that 9.81 was. So if we take an object and we're holding it at rest, time 0, no velocity. But after 1 second, we're going to be negative 9.81. After 3 seconds, negative 29.43. But in 5 seconds of free fall, it's going to be moving at negative 49.05 meters per second. What's that equate to in miles per hour? In about 5 seconds of free fall, an object's going to approach about 110 miles per hour. If an object is thrown horizontally, at the same time something is dropped vertically, which one's going to hit the ground first? Well, when I let go of something thrown perfectly horizontal, at the same time something is dropped, the minute each one leaves my hand, the only thing affecting it is going to be gravity, and figure 11 in your book shows this, but they will hit at exactly the same time. So if all objects are accelerated by gravity, do all objects fall at the same rate? Meaning that if I were to take this steel ball and I was to take a Kleenex, will they hit the ground at the same time? In or on Earth? Well, the object is no. And the reason why is because of air resistance. You know that if you take a hammer and a feather, drop them at the same time, that hammer is going to hit first because, again, of air resistance. As we're dropping it, air is pushing back up. Hammer is heavier, feather is lighter. So therefore, that air resistance is going to affect the feather more than the hammer. But on Earth, we deal with air resistance. On the moon is where we would have that free fall occurring. Air resistance is a specific type of fluid friction that has air pushing on an object. It's going in the opposite direction. So like I said, if something's falling, air resistance is going to be up. If we're talking about a car driving on the road, if it's traveling north, the air resistance or the friction is going to be south. So again, it's still opposing the motion of an object. Terminal velocity, that's the maximum velocity an object will reach during free fall. Okay, in the presence of air resistance. When I drop that hammer, it's going to go faster and faster downward. When I drop a Kleenex, all of a sudden you kind of see it swaying back and forth. That's because it has reached its terminal velocity sooner than what the hammer reached its terminal velocity. Let's talk about mass and weight. It is something that we have technically talked about already. A special type of force that's related to mass is the object's weight, and we talked about weight depending on gravitational forces. It is the measure of the gravitational pull acting on an object's mass. Mass, remember, is the amount of particles in an object. The amount of particles in an object will not change whether it be on Earth, whether it be on the moon, or whether it be on Jupiter. But weight will change because gravity is different on the Earth, on Moon, and on Jupiter. What is the equation for weight? Weight is going to be equal to mass times gravity. W equals mg. Now, in your circle equation, okay, if you go ahead and draw up your circle equation, weight will be on top, mass and gravity will end up being on the bottom. Now, I want to bring you back here to that equation. That is not a negative symbol. Okay, that is not negative. That's just me tabbing in here. But weight will be measured in newtons. Mass will be measured in kilograms. Gravity is going to be whatever the gravity is wherever we are at. If we are on Earth, you will use that negative 9.81 meters per second squared. If we're on the moon, where it is 6 times less, you will use 9.81 divided by 6 because it is 6 times less. Weight changes because of gravity. Mass is always the same each and every place. Now, when we're talking about gravity, if we talk about a gravitational pull is going to exist everywhere. All objects are going to be attracted to one another. They exert a force and attraction to every single thing, and that's explained by the universal law of gravitation. There's two factors that are going to affect how much gravitational force exists between two objects. The first one's going to be mass. Heavier objects exert more attraction, exert more gravitational force. Lighter objects are going to exert less force. And the second one's going to be distance. Think of magnets. The closer two magnets are, the greater the attraction will be. But if I spread them out, if I have a greater distance, the gravitational force is going to be less between the objects. The heavier the objects are, the more force exerted. Therefore, mass and gravitational force are directly related. The closer the objects are, the more force exerted. So therefore, you're going to find out distance and force are going to be indirectly related to one another. The last section is going to be talking about a centripetal force. That's going to be talking about some satellites, some natural satellites and some man-made satellites. A satellite is just going to be any object that travels around another object in space. For example, the Earth travels around the Sun. The Earth is going to be a natural satellite of the Sun. The Moon travels around the Earth, so therefore the Moon is going to be a natural satellite of the Earth. But if we put something out there like a telecommunication satellite and it's traveling around the Earth, that's just going to be a man-made satellite, but it's still traveling around the Earth. Weather, military intelligence, communications, those are all satellites that we have orbiting around the Earth that are going to help us with some sort of communication. Satellites in space, they're constantly orbiting the Earth. What keeps them from flying off into space? Because technically they're trying to go off in a straight line. But Earth's gravity is always pulling it back in. So as it moves forward, Earth causes it to pull down. As it's coming down, Earth pulls it back in. So Earth's gravity keeps it in that orbit, keeps it in that circular motion. And that circular motion, that's going to be centripetal force. It's the force that keeps an object moving around another object, or orbiting, circling an object in space. It's always directed towards the center of the object that it is orbiting. Okay? So centripetal force is any force that keeps an object moving in a circle. So as we talk about the Earth here, and as that moon is going around the Earth, centripetal force, don't say downward, because here it's directed towards the center of the Earth. Down here it's directed up towards the center of the Earth. So the satellite is always, the centripetal force, always directed towards the center of the circle or towards the center of the object that it is orbiting. Your assignment is to read pages 323 to 329. Also, the last section, 338 to 340. Questions 1 through 4 are on page 329, and questions 1 through 4 are on page 340.